Antiderivatives and indefinite integration. Suppose you are asked to find a function, capital F, get used to that, whose derivative is f of x equals 3x squared. From your knowledge of derivatives, you would probably say that capital F of x equals x cubed because the derivative of x cubed is 3x squared. The function capital F is an antiderivative of f. So when we see something like this, if we have a function f of x equals x cubed, and we take its derivative and we get 3x squared, we've been calling the 3x squared the derivative of f of x. Well, now we can call f of x the antiderivative of f prime of x. This book and most books tend to use that capital F to signify antiderivative. Okay? So we could think of it this way. If this is f of x, then this is capital F of x. All right? Definition of an antiderivative. The function, a function, capital F, is an antiderivative of f on an interval I if the capital F prime of x equals little f of x for all x in I. Boy, that got complicated, didn't it? A function is an antiderivative if, when you take its derivative, you get the function you wanted the antiderivative of. Yeah, it is. It's a circle. The reason it's a circle is because an antiderivative is undoing what we've spent all year doing so far, right? It's just going backwards. It's like when you learned multiplication, then all of a sudden the next day you learned division. It was the inverse of multiplication. We've been doing derivatives. Now we're learning how to do antiderivatives. They're the inverse operation of doing derivatives. Let's keep going. Note that capital F is called an antiderivative of f rather than the antiderivative of f. To see why, observe that antiderivative, that antiderivative, that antiderivative are all antiderivatives of that. How do I know? Because if I take the derivative of x cubed, don't I get f of x? If I take the derivative of x cubed minus 5, don't I get f of x? If I take the derivative of x cubed plus 97, don't I get f of x? In fact, for any constant c, the function given by capital F of x equals x cubed plus c. Now, c can be negative, even though it says plus c. It could be like plus negative 5, all right? So any of these, capital F of x equals x cubed plus c, is an antiderivative of f. All right, so our theorem, 4.1, representation of an antiderivative. Notation is an issue here, so think with me. If capital F is an antiderivative of f, then g is an antiderivative of f if and only if, I should say capital G actually, then capital G is an antiderivative of f if and only if capital G is of the form where it's capital F of x plus some constant. Okay? So once you find an antiderivative, you can find as many antiderivatives as you want simply by adding a different constant at the end. That's what they did here, isn't it? Mm-hmm. Yep. So, my notes. Any function has more than one antiderivative, and these antiderivatives differ by a constant. All the variable expressions will be exactly the same, but they will differ by a constant. All right, you still hanging in there? All right, using Theorem 4.1, You can represent the entire family of antiderivatives of a function by adding a constant to a known antiderivative. That's what I said. For example, knowing that the derivative, look at the notation, the derivative of x squared equals 2x, you can represent the family of all antiderivatives of f of x equals 2x by capital G of x equals x squared plus c, where c is a constant. The constant c is called the constant of integration. So c has a name. It's the constant of integration. The family of functions represented by g is the general, so here's where that's why they used a g, is the general antiderivative of f. And capital G of x equals x squared plus c is the general solution of the differential equation. G, capital G prime of x equals 2x. All right, we'll come back to differential equations in just a minute. So when you have the plus c on there, it's a general antiderivative, not a specific or not a particular antiderivative. We'll get to those eventually too. So when you don't know what the constant is, it's a general antiderivative. If I know what the constant is, like I do here, now it's a particular antiderivative. Lexi? Yeah. Yep. All right. A differential equation. That's why it's called a differential equation. Derivatives in it. Okay? Differential equation in x and y is an equation that involves xy and derivatives of y. So, for instance, y prime equals 3x is a differential equation. Why? It's got a derivative in it. Y prime equals x squared plus 1 is a differential equation. Why? It's got a derivative in it. Okay? And the way you solve differential equations is by finding an antiderivative. More notation issues. When solving a differential equation of the form dy dx equals f of x, so they're using dy dx as opposed to using y prime, okay, or f prime of x. It is convenient to write it in the equivalent differential form dy equals f of x dx. Now, that's actually a definition of this equivalent differential form. It's actually a definition. But you can see it's a trick. It's not really algebra because dy dx doesn't mean the letters dy divided by the letters dx, does it? It's just a notation for a derivative. However, one of the good things about this notation is it appears that all I have to do to go from there to there is multiply both sides by dx. So that notation is handy because it makes you remember this. Okay? It's not really algebra, but it looks like it. So a long time ago, you know, people figured out, hey, it looks like that works. Let's just pretend that it does. We'll tell students that. They'll fall for it, and they'll do what we tell them to do. Well, I don't want to trick you, so I'm telling you it's not really algebra, but it sure looks like it, doesn't it? Okay? All right, so the operation of finding all solutions of this equation is called antidifferentiation or indefinite integration. The term antidifferentiation and the term indefinite integration, and there's something called definite integration as well, so the word indefinite matters, are the same idea. Okay? Finding an antiderivative and finding an indefinite integral are the same idea. Okay? Now, first day we talked about two types of calculus, differential and integral. We've been doing differential. Guess what we're getting ready to go to? We're getting there. And how do we get to integral calculus? Through antiderivatives. Okay? All right. Either way, antidifferentiation or indefinite integration, they're both denoted by what is called an integral sign. It's supposed to look like an S that gets stretched out. It doesn't to me, but that's what it's supposed to look like. The general solution is denoted by, that means written as. All right, so here we go. Y equals the integral, maybe I should highlight this as I go. Y equals the integral of f of x dx. Now, f of x is called the integrand. Dx is called the variable of integration. It's very, very important that the function has the same variable as that. And I know you're thinking, well, of course it will. When we get to applications, we've really got to make sure that our function is of the same variable as our variable of integration. Okay, it becomes an issue. So right now, it's not really going to be, but it becomes an issue. So pay attention to that. Equals capital F of x plus c. C, like we said before, is called the constant of integration. And what else have we called that? We've called that the general antiderivative, didn't we? So the indefinite integral equals the general antiderivative. The indefinite integral equals the general antiderivative. The expression, the integral of f of x dx, is read as the antiderivative of f with respect to x. Now, it's supposed to be read as, just like when we see this, it's supposed to be read as the derivative of y with respect to x. But what do we all say? We all say the derivative. So we'll leave that off when we say it, but you've got to know that matters. Okay? If it was the integral of f of t dt, that would be the antiderivative with respect to t. Okay? So I'm not going to make you say that every time because I don't want to say it every time. Nobody says it every time. But you got to know the variable matters. Okay? All right, you still hanging in there? The inverse nature of integration and differentiation can be verified by substituting capital F prime of x for f of x in the indefinite integration definition to obtain. So let's wait just a second. Does it make sense that we can substitute one for the other? If we're going to substitute one for the other, they have to be equal, don't they? Well, they are, aren't they? They're just different notations for the same thing. Because recall, here's what we've been doing all year long. We'd do that, then we'd find its derivative. Now we're just changing it to saying that. Okay? So the derivative of this does give us f of x. All right. Now, here's what this says. The integral of capital F prime of x dx equals capital F of x plus c. Now, I personally would have just amongst the conscious maybe. All right. I would have no problem with this to say the integral of regular f of x dx equals capital F of x plus c. In fact, I think that's a little more natural to look at because we're saying that the antiderivative, indefinite integral means antiderivative, that the antiderivative of f of x is called capital F of x plus c. What they wanted to do is they wanted to replace f of x with capital F prime so that you would see that the integral sign and the derivative notation are inverse operations, leaving you with what you started with. It's kind of like if I took something like this, and I squared it, and then I took the square root of it, wouldn't I be back right here? Same idea. I start with capital F, and I take its derivative to get this. So I started with capital F, and I took its derivative. Then I took the antiderivative of that. Doesn't that get me back to where I started? The only difference is, since I took the antiderivative, antiderivatives can differ by a constant. So I got to put the plus C at the end. Did you follow me? Get the inverse operation idea? Okay. Now, if I had this again, and I took its square root, and then I squared that, wouldn't it still work out that way? So if I start with, all right, now they're messing with the capitals and the little f's with me again. But if I start with, regular f of x, and I find its antiderivative, whatever that antiderivative is, but then I take the derivative of the antiderivative, I end up back where I started. Now, this one has a plus C, this one doesn't, because it depends on when you do the antiderivative step. Here we did the antiderivative step first, so when I took the derivative of that C, what's the derivative of a constant? 0. So I'm not going to put plus 0, am I? But here I did the derivative first, and when I take the antiderivative of that, that's when I got to put the plus C. So that's why the C's on one, not on the other. So what you really need to know right now is that derivatives and antiderivatives are inverse operations. You also need to be aware that notation can become an issue. Okay? So try to do your very best to use the proper notation, because it's going to be an issue if we're not careful. All right. If I take the derivative of the antiderivative, what do I get? The function. If I take the antiderivative of the derivative, what do I get? The function plus C, because I took the antiderivative last. Okay? All right, so my notes. Integration, which is anti-differentiation, is the inverse operation of differentiation. And differentiation is the inverse operation of integration. So integration is the inverse operation of differentiation, and differentiation is the inverse operation of integration. And that leads us to this. Integration rules, and again, integration and antiderivatives, or integration and anti-differentiation, same words, or different words for the exact same meaning. So integration rules are the derivative rules in reverse with opposite operations. Now, I actually mean that. Okay? You do the operations in reverse, and you do the opposite. So, for instance, the power rule for differentiation says that you multiply the exponent times the coefficient, then you subtract 1 from the exponent. So we've got to do it in the opposite order with the opposite operations. So we multiplied first, then we subtracted. So we got to go the other way around. We've got to, what's the opposite of subtracting 1 from the exponent? Add 1. So we got to add 1 to the exponent, and then what's the opposite of multiplying the coefficient by it? Dividing it by it. So we add one. So the power rule for integration is add 1 to the exponent and divide your coefficient by that. Okay? So the integral of x to the n dx, the dx matters, don't leave it off, equals, all right, add 1 to the exponent. So we add 1 there. Then we divide the coefficient by that. So we divide by n plus 1. Don't forget, plus c. So the power rule for integration is to add 1 to the exponent and then divide the coefficient by that. Divide the coefficient by the new exponent. Plus c. All right, brace yourself, because here are your new integration rules. All right, this is all on page 250. On the left are the derivative formulas that you're already familiar with. On the right are the equivalent integration formulas that you're going to become familiar with. Okay? All of these are also on that cheat sheet I gave you finally after talking about it for a month or two that I finally gave to you. They're all on there. Okay? So you're going to have to know these. All right. I need you to look at example 3 on page 251. Like we did with derivatives, especially when we first started derivatives and we didn't know very many methods, quite often, I mean, we only got one method and then a whole page of formulas. We've got the power rule for integration and then a page of formulas. If our problem doesn't fit the power rule or one of those formulas, we've got to rewrite it so that it does. Okay? So there are actually, I call it example 3, but there are actually 3 examples there in example 3 that I'm going to let you look at on your own time. And then on page 255, we have the same idea again right before they give us the problems to work, where they have 4 of them this time, where you have to rewrite so that you can actually work the problem. So, if you're faced with an integration problem or an anti-differentiation problem, and you look at the function and you're like, well, I have no idea how to do that, rewrite it. Turn it into something that you know how to do. We're good with polynomials. Polynomials were easy to take derivatives. They're easy to take anti-derivatives because you just use the power rule for integration. Okay? So polynomials are good. All right? To solve a differential equation, and this was in the book, and I had it on a screen, but not for very long. Write your differential equation as dy dx equals f of x. Pretend that you're multiplying both sides by dx to get dy equals f of x dx. Then you take the antiderivative, the indefinite integral of both sides. As you probably know, you can do pretty much anything you want to an equation as long as you do it to both sides. Okay? Now, on the left, the integral of dy is y, because that means the integral of the derivative of y, well, the integral of the derivative of y is y. So you get y on the left, and then you just got to work out the right. That's what we're going to start learning how to do, is working out the right side of this equation. All right, we're going to learn how to get the integral of f of x dx. And we'll call it capital F of x plus c. And look how excited I was when I wrote, now let's do some examples. I even put an exclamation mark there. On page 255, let's begin with number 3. Verify the statement by showing that the derivative of the right side equals the integrand of the left side. So they're not asking us to figure out the integral yet. They're trying to get us to see the relationship. If I take the derivative of the right side, because what we're saying is this. When we say the integral of, and then what I just underlined in red would be f of x equals, and then this would be our capital F of x plus c. When we say that's true, we're saying that the right side is the antiderivative of the integrand. Well, if I take the derivative of the antiderivative, I got to get back the integrand, the function. Okay? So, all we got to do is verify it, so we know it's going to work. So, all we got to do is take the derivative of the right side. So, we're going to take the derivative, and it's with respect to x. If I didn't know, I would know because of the dx. Okay? So, take the derivative with respect to x of 1/3 x cubed minus 4x plus c. All right. Plain old derivative. Thing we've been doing for a long, long time. What's the derivative of 1/3 x cubed? X squared. And the derivative of negative 4x is negative 4. And the derivative of any constant is 0. No need to write plus 0. All right, so far, though, the derivative doesn't look like the integrand. What do I need to do to x squared minus 4 to make it look like the integrand of the left side? Factor it. And we've done it now, haven't we? We good with number 3? Number 8. Find the general solution of the differential equation and check the result by differentiation. So we're supposed to find the general solution of this differential equation. So we've got it written in the proper form. dy dx equals 2x to the negative 3. Multiply both sides by dx. And now we've got dy equals 2x to the negative 3 dx. I can do whatever I want to an equation, mostly, as long as I do it to both sides. So take the antiderivative of both sides, the integral of both sides. Bless you. What's the integral of dy? Y. And what's the antiderivative of 2x to the negative 3? Use the power rule for integration. Add 1 to the exponent. So if your exponent's negative 3 and you add 1 to it, now it's a negative 2. Then you divide your coefficient by the new exponent. So divide that 2 by negative 2. And when I divide 2 by negative 2, I get negative 1. So that's how I get negative x to the negative 2. Don't forget, plus c. And the only thing I would do to that is, we're not real fond of negative exponents. So make it y equals negative 1 over x squared plus c, and we're good. Now, they also wanted us to check the result by differentiation. In theory, you can always do this. Once we get to complicated stuff, it doubles your work. It's not worth the time. But since this is the first time we've done this, let's talk about this. I ought to be able to take the derivative of my antiderivative and get the function back, shouldn't I? Okay? So if I take the derivative of my antiderivative, well, the derivative, write the negative 1 over x squared like we had it before, and then take the derivative. You would power rule that. It'd be exponent times coefficient. That'd give you a positive 2. X, subtract 1 from the exponent. Negative 2 minus 1 is negative 3. The derivative of any constant is 0. So we've got it right. Make sense? All right. Number 11. Which leads us to a potential problem, right? You'll be going along doing integration, and then all of a sudden you just, for some silly reason, do a derivative step when you should have done an antiderivative step. It happens. I do it too. You just got to watch out for it. All right, number 11. We're going to need to rewrite this thing so that we can find its antiderivative. All right, so first of all, the radical notation's got to go, right? So let's write that x times the square root of x. Think of that as x times x to the 1/2. X times x to the 1/2 is x to the 3/2, isn't it? So the first step was to get rid of the radical notation and put it into exponential notation. But we don't have, and in fact never will have, any type of quotient rule for antiderivatives. So we can't handle that because the x is in the denominator and we can't handle it. We just can't. All right, but if I make that x to the negative 3/2, I solve that problem, don't I? And now can I use the power rule for integration? I can. So we've got the integral of x to the negative 3/2 dx, or the antiderivative of x to the negative 3/2 dx. Power rule it, but it's the power rule for integration. So you add 1 to the exponent first. What's negative 3/2 plus 1? Negative 1/2. And then we divide our coefficient by negative 1/2. Now look, dividing by a fraction is the same thing as multiplying by its reciprocal, isn't it? Dividing by negative 1/2 is the same thing as multiplying by the reciprocal of negative 1/2. So it's the same thing as multiplying by negative 2. That's going to happen a lot. We got to get good at that. Okay? Don't forget, plus C. And, you know, I'm fairly happy with that. I don't like the negative exponent, though. And I'm really happy with that. But if I can, since my problem started with radicals, I'd rather end with radicals. Now, we'll face problems later on that are just so complicated, we won't bother putting it back into radical form. But this one's not an issue, so put it back into radical form. We okay with 11? All right. 13. We need to rewrite this one too. Now, we just got through talking about how we can't handle the x being in the denominator. So I know I need to make that an x to the negative 3. But be careful. The 2 stays in the denominator. Okay? Don't move the 2 with it. Only take the x to the negative 3. So rewrite that as the integral of 1/2 x to the negative 3 dx. You follow me on that? How the 2 has to stay there? The 2 doesn't have a negative exponent on it, or an exponent at all on it. Okay? You with me on the rewrite? All right, work that out. See what you get. All right. Let's go on to number 28. Now, they didn't give us the little gray boxes to show us that we need to rewrite it, but we need to rewrite this one, okay? And we're going to rewrite it with division. So that you would read this as the integral of x squared plus 2x minus 3 all that divided by x to the fourth dx. So let's do the division. X squared divided by x to the fourth would be 1 over x squared, but instead of writing it as 1 over x squared, write it as x to the negative 2. 2x divided by x to the fourth would be 2 over x cubed, but a better form would be 2x to the negative 3. And negative 3 divided by x to the fourth would be negative 3 over x to the fourth, but a better version is negative 3x to the negative 4. And like with derivatives, how we could just take the derivative of each term of a polynomial, we take the antiderivative of each term of a polynomial. Well, with negative x, we can take the antiderivative of each term. All right, so what's the antiderivative of x to the negative 2? Add 1 to the exponent, divide the coefficient by that new exponent, right? What's the antiderivative of 2x to the negative 3? It's that exponent you got to get negative. Add 1 to the exponent, makes it a negative 2. Now divide your coefficient by that new exponent. What's 2 divided by negative 2? That gets us there. And what's the antiderivative of 3x to the negative 4? Add 1 to the exponent, divide your coefficient by that new exponent. Negative 3 divided by negative 3, positive 1. And what have I left off? Should we leave the negative exponents in our answer? No. But I'm not going to make you add those fractions together. $39. We have the integral of secant squared theta minus the sine of theta d theta. Wow, I really hope that page 250 contains a formula for the antiderivative of secant squared theta. I don't know why it would. Why would we know the antiderivative of secant squared theta? Do we know the antiderivative of secant squared theta? Tangent theta plus c. And the reason we know this is because it's a derivative formula backwards. The derivative of tangent is secant squared. Therefore, the antiderivative of secant squared is tangent. Okay? So the antiderivative of secant squared theta is the tangent of theta. And like Blake said, plus c. Hang on to that plus c thought. And we copy down the minus sign. And then what's the antiderivative of sine? Well, the antiderivative of the sine of theta is negative cosine of theta. Now, why is it negative? Well, because the derivative of cosine is negative sine. So the antiderivative of negative sine would be positive sine. So the antiderivative of sine is negative cosine. I missed a cosine in there somewhere in that. But anyway, okay? And then there would be another plus c, correct? And I should have talked about this on 28, but I didn't think to. So if there would be a plus c when I find this antiderivative and a plus c when I find this antiderivative, how come I only wrote 1 plus c? Exactly. Add the two c's together. I don't know what they are anyway. Add them together and just get one of them. And then I don't like the minus negative, so there's our answer. Eventually, you got to memorize the formulas for the antiderivatives of these trig functions. But eventually is not right now. Okay? Look them up. We okay with 39? Let's take a look at 40. Yeah, it's only one harder. Boy, it looks worse. So I look on page 250. Do I know, oh wait, even if I knew those antiderivatives, they're multiplied out. And remember how with differentiation, the derivative of two things multiplied was not just the derivative of one times the derivative of the other? Same thing with integration. So even if I knew the antiderivative of secant of y or the antiderivative of tangent y minus secant y, I can't just plug those antiderivatives in. It doesn't work that way. Distribute the secant y. So we've got the integral of secant y tangent y minus secant squared y dy. Right, that I'm going to look up. Do I know what the integral of secant y tangent y is? What is it? It's secant y. Do I know what the antiderivative of secant squared y is? Tangent. So, the antiderivative of secant y tangent y is secant y. Copy down the minus sign. The antiderivative of secant squared y is tangent y. Don't forget, plus c. And your assignment. Page 255, 1 through 41 odd.